An astronaut is being tested in a centrifuge. The centrifuge has a radius of 10 meters, and in starting from rest, it means initial velocity equals 0. Also means that angular velocity equals 0. Rotates with uniform angular acceleration according to omega 0.6 t, where t is in seconds. So basically it's accelerating. This, when t equals that, okay, so what is its angular velocity, where t is in seconds, gives radians per second, when t is 5 seconds. Oh, when t equals 5 seconds, okay. So this is a kinematics equations. So first thing I'm going to do is I'm going to start by writing out my kinematic equations. I'll do it over here. A equals a, that just means acceleration is constant. V equals at plus v naught. X equals 1/2 at squared plus v naught t plus x naught. And then v final squared equals v initial squared plus 2a delta x. I know my v's look kind of like u's. And then your first thought after this is, well, we're not dealing with linear. These are angular, which is true. So I'm going to look at the conversion factor between angular and linear. So I always start off with x equals r theta, and I do this in terms of I think of it in terms of like a circle. So we have a circle, and if we go around the circle, like so, that distance is going to be the perimeter of a circle. And I just have it memorized, as most people seem to, that's 2 pi r. 2 pi r is the circumference of a circle. Well, if you go around the circle in an angular fashion, then the angle you're going to go around is 2 pi, r is r, you put 2 pi and r together and you get 2 pi r. Makes sense that the left side and the right side are the same, so you're like, that might actually be true. And then we just follow the same format for angular, for velocity. V equals r omega, and acceleration equals r alpha. Angular speed and angular acceleration. And then one more step, and I know it feels like a lot of prep work just to write up the formulas. It is. I like to do this if I have time, whenever I'm working through things. If I'm doing this like on timed evolution, I'll write it up for one problem, and I'll just keep referring back to that one time. So we're just going to write up the angular equivalent. We're just going to replace a with alpha, v with omega, and x with theta. So this becomes omega equals alpha t plus omega naught. Theta, angle, equals 1/2 alpha t squared plus omega naught t plus theta naught. And omega final squared equals omega initial squared plus 2 alpha delta theta. All right, so now we have everything together. We want to put this together. All right, so what's angular velocity? And specifically, it's asking for the final angular velocity. So I'm going to use this equation of all these equations over here, which I guess is like 11 equations. That seems like a lot. That's okay. It's not really 11 equations. It's a couple. All right. So they want angular velocity, specifically final angular velocity, which is going to be, they don't give us the angular acceleration. Oh, they sort of do. So, okay, game face, focus, a couple ways of doing this. They say omega as a function of t equals 0.6 times t. One thing you can do with this, now we could just skip to end and totally fair, is we could say that alpha is the derivative with respect to time of omega. The angular acceleration is the derivative with respect to time of the angular speed. The derivative of 0.6t is just going to be 0.6. So we'll be like, oh, alpha is 0.6. Since it is constant, the kinematic equations apply, and we could just say omega final is 0.6 times t plus omega initial, which we know is 0. So this is going to be 0.6 times 5, which is 3 radians per second. Or it could be like, they just give us the angular speed for any given point in time. Omega final is 0.6 times 5, which again is 3 radians per second. So if we wanted to, we could make this first part really hard, or we can just use the information they gave us and take the easy path that they intended. So long story short, either way is correct. And the reason that I was able to find the angular acceleration here and then use the kinematic equations is because the angular acceleration was constant. You need constant angular acceleration for the kinematic equations to work. So, and that just goes to the idea of you take your constant angular acceleration and you take the integral each time. So, easy problem that I was able to make difficult. All right, part B, linear speed. So linear speed, we're just going to use this equation over here. This is the conversion between linear and angular. This only applies when you don't have, when you have angular or rotational. When you have a mix of the two, these don't apply. So like when you see like a question where they're talking about like something rolling down a hill, if you see the phrase rolling without slipping, then like, oh, this conversion applies. So the linear speed equals v equals r omega. At t equals 5 seconds, we're going to use our previous value of 3 radians per second. So the centrifuge has a radius of 10, so it's going to be 10 times 3, which is 30 meters per second. Radius 10, angular speed 3 from our previous problem. Bam. Angular acceleration. So the angular acceleration, we already found that by doing the derivative. Yes. Yes, so we found it by, they gave us a formula, omega equals 0.6t, take the derivative of both sides with respect to t, d dt. The derivative of linear speed is angular acceleration. We get 0.6 radians per second squared. Another way of doing that, if we wanted to decide we wanted to use the kinematic equations, is we could take this equation right here, rearrange it. This is actually omega final, even though I just write it as omega, is omega naught over t, which is, we decided, and this is kind of working backwards. So this is going to be 3 minus 0 over 5, which gives us 0.6 radians per second squared. And what this is actually doing is when we use this equation, we assume a constant acceleration. Did they say use the word constant? Uniform. Uniform angular acceleration. Uniform means constant. So what this equation is actually doing is it assumes a uniform acceleration, a constant acceleration. And so when we solve it, what we're actually doing is we're finding the average. And if it's uniform, then the average and the actual are the same thing. If for some reason we assume it's constant, but the angular acceleration is not actually constant, then we just found the average. So keep that in mind, not a big deal. Tangential acceleration. All right. So I'm going to draw a picture here. So we have astronaut going like so, more actually circular, not drawn to scale. And we want to find out how much his speed is changing. So what I'm going to do is I'm going to find out his linear acceleration. So from their equation over here, a equals r alpha. This is going to be r, which is 10, times alpha, which we just found, which is 0.6. So this is going to be 6 radians per second squared. So the linear acceleration, I'll do a little a with t underneath it to mean tangential, which is the same as linear in this case. And then radial acceleration. Now, this is going to be a little bit different. So the acceleration, you have acceleration tangential, and we have acceleration radial. I know this is supposed to be at the edge of a circle here. Since mine, I drew kind of an oval, it makes it look funny. Not supposed to look funny. Acceleration, or velocity, is a vector, a little vector. And a vector has both magnitude and direction. So tangential acceleration is going to change the magnitude, how long the arrow is. And radial is going to change the direction. So if you have a velocity going this direction, and then afterwards, a little while, you have a velocity going this direction, arrows might be the same size, but they're pointing different directions, and acceleration occurred. So the radial acceleration, that's what the radial acceleration is. Not going to derive the formula, I'm just going to throw it up there and be like, this is the formula. So acceleration, I'm going to use c for centripetal because that's usually what you see it as, but radial, same thing. It's causing it to rotate around a circle. It's going to be v squared over r. We know that velocity, linear speed, is 30. So we're going to do 30 squared over radius, which is 10. So 30 squared is going to be 900. So 3 squared is 9. The little 10 squared is 100. 900 over 10. We get 90 meters per second squared, which seems like a lot. Meters per second squared. All right, so let's try this a different way. We used angular, so what if we instead used acceleration centripetal, and we said v is r omega. So we're going to say, instead of velocity squared, use r omega squared over r. I know up here I used big R, this little r, they're the same r. Omega squared r, I know I'm switching back again. It is terrible. I am sorry. One of the r's cancels, then we get omega squared r. So now if we plug values into this, omega, we said was 3. So if we do 3 squared times r, which is 10, we get 9 times 10, which is again 90 meters per second squared. So this, I just did it that way to show that if for some reason velocity linear and velocity angular, you can use either one. And sometimes it'll be more convenient to use one, sometimes it'll be more convenient to use the other. They're the same formula, they're both true. So for that, the answer would be 90 meters per second squared, which is a lot. It's like, I don't know, 9 Gs? Yeah, probably 9 Gs, that's a lot. Many Gs. All right, so I hope that helped. See you next time.